I'm Bob Hauge. I'll be moderating this afternoon session, and I'll try to keep my time spent up here very short. Read your title and read your speaker. And we're going to continue. We're obviously running behind the times, but we're going to give everybody their full allotment of time and hope you can stick it out through the course of the afternoon. So this afternoon, we'll start with The Challenge for the Grid of the 21st Century by John Stringer.
Thank you. Okay. Nice to be here. And it's nice to be here, particularly since I'm going to be talking about the grid. I was here in, I guess it was May of 2003, the previous meeting, where Rick had asked me to come along and talk about the grid. So I thought to myself, and indeed somebody asked me on the way in, has anything much changed in the last 2 years? And I suppose the answer is not very much, but we'll see. And the other thing is that, of course, one of the things that changed is, as I say, it was May of 2003. And in August of 2003, the East went black. So that I suppose one can say that there's something changed, but only in the magnitude, and you've heard a lot of talks about that. This is just one of these pompous things that one says at the beginning of this whole thing about the way in which the electricity industry has developed in this country. Edison, of course, and Sam Insull were operating at the latter part of the 19th century, and Sam in particular was the person who developed the really large industry. Looks much like what we were doing now, and was interested in getting electricity through to a rather large group of people around Chicago. Largely, the delivery has been AC, alternating current, for reasons that we'll get to, and the delivery system that takes the electricity from the generator to the customer is called the grid, of course. I'm going to be concentrating mainly, in view of what we heard at lunchtime, on the big grid. It's not because I haven't worked on the small grid, but I just chose today to think about the big grid, so sue me. Now then, as you've heard, the North American grid comprises three separate components, which are called the interconnects, as you know. The Eastern, which covers 2/3 of the United States and Canada. The Western covers most of the rest of the two countries. And the Electric Reliability Council of Texas, covering most of Texas, but as you heard, not quite all of it. Within each interconnect, the power flows through AC lines. And one of the points of this is so we can synchronize these all tightly to the same 60 Hertz cycle, and that is actually rather important. Now then, between those three different organizations, however, there is no synchronization to the same level, but there is transfer of power between those three interconnects, and that wasn't, I think, once or twice I heard remarks by people who didn't apparently know that happened. And that exchange of power between it, because there is no synchronization, a lot of that power goes with high voltage DC, and I'll have something to say about high DC later. Okay, the transmission, as you see, which is around about where it's generated and where it's used. And here's some numbers. The average power plant size in the US, average, in 2002 was 300 megawatts. The total installed generating capacity at that time was 981,000 megawatts. If the power plants ran full time, the net generation would be the numbers on there. The actual net generation, the amount used, was only about slightly less than half of that. The reason for that, of course, is because we have a need for generating capacity that will deal with the maximum power required, and that maximum power required is only required every so often. You can't really reduce that capacity factor by very much. With some of the market forces that have been applied over the last half a dozen years, there's been a tendency to allow, in some cases, that margin to diminish. And that's a dangerous thing to do. It's rather important to make sure that one has adequate capacity that will also allow the possibility, because since I did that sum very simply, so I told you what the maximum installed amount was, but of course if any of these plants at any time, some of the plants are down for maintenance and that kind of thing. And that's just about the mean annual power consumption. Again, doing this as simply as possible. The power is generated at voltages around about 25 kV, but in order to operate the grid system, it's necessary to try and increase the voltage to reduce the current, and that means that the thermal loads on the whole system are kept fairly small. The AC, of course, enables you to do that. With DC, it is more difficult, although not impossible. Typically, the transmission is carried out over overhead conductors, of course. The total range for these in the United States is around about 110 kV to a maximum of 765 kV. And the US operates about 157,000 miles of high voltage. That's more than 230 kV of these lines. I thought you might be interested. The highest voltage line in the world is in Kazakhstan, from a place that I can't pronounce to another place I can't pronounce. A distance of 268 miles is 1150 kV. Why do we not all go at that? And that's because of the nature of the losses in these systems. The transmission losses at the voltages that we use at the moment are mainly thermal losses. However, as you get the power up, you start to get corona losses occurring, and that starts to become a major problem once you get around about 2000 kV. All right. Somebody at these meetings always says, how much do we lose in the transmission system? And there are the numbers. It was about 5% in 1970, rose to 7.2% in 1995, and grew to 9.5% in 2001 due to heavier utilization and more frequent congestion for reasons that you are totally familiar with. The capacity limits on transmission are largely set, as I said before, by temperatures. If the temperature gets too high in the conductor, in the line, it gets warmer, and if it gets warmer, it sags. That can be a nuisance. As I said, in the worst case, it may contact trees even. It can even contact the ground under some special circumstances. And one of the ways of increasing the capacity would be to increase the strength. I put that in because I said that in 2003 when I was actually looking at the effect of nanotechnology, and we have been looking, as many of you know, at ways of getting conductors that can transfer these high voltage signals which are stronger and lighter. And Rick was always keen to point out to me that he was sure he could achieve that in no time at all. Another limitation on this, of course, is the mechanical strength of the support structure. These are high pylons. The high pylons are high for a number of reasons, not least of which is to reduce the corona loss to the ground. And people don't like those. C'est la vie. I thought you might also be interested to see what the capacity limits are for AC transmission lines. Once again, there's been some comments of that as we've been going through this thing today. And these are the kind of limits that we have. For the 765, that's the highest current, the highest voltage that we use typically. If the length is only 100 miles, then the maximum capacity of the line can be 3.8 gigawatts. If it goes up to 400 miles, that drops to about 2 gigawatts. And I put the numbers up for the other things, and I've also shown you what the reference is for that. Okay, now the thing is that you can, however, use high voltage DC in some situations, and if it's going to be moved over long distances, it can be more economical to transmit using DC. You can get smaller losses, and you can get reduced construction costs for these, and that can balance the cost of the converter stations you need at each end. And there are some specific places where HVDC is the preferred option. Undersea cables, the 250-kilometer Baltic cable between Sweden and Germany is an example of that. And you may have heard recently in the press the idea of building a line, an underwater line down to California from some point to the north. And the intention is at the moment that also will be a DC, an HVDC line. And there are a number of other places. Interestingly enough, worldwide there are quite a lot of these things, and the Chinese, and people have been talking about the Chinese power system recently, and they have quite a number of quite long high-voltage DC lines, particularly in looking at the movement of power from the new large hydroelectric schemes that they have in China. So don't forget HVDC. We don't talk about it much at these things, but it is a significant actor, and it may become more so. Okay. The thing is that, as you know, and as you heard, the way the transmission system, the high-voltage transmission system was built, the general idea was we wanted to have fairly large power plants, 300 megawatts, and we wanted to have it was more sensible in many ways to locate these close to where the fuel was cheap and then move the electricity from there to where it was going to be used. That's the underlying basis for having a transmission system at all. And the transmission system, however, as again you've heard, was designed and considered to be really the kind of thing that you needed to shift it from a 300 megawatt generator to the audience base, the customer base for that. And the idea of transferring large amounts of energy, which is what's being done now, was not the original basis of the design. It's interesting that it can still manage to do it reasonably well, but it's not a fault that it can't. It wasn't supposed to. If you're going to look at this as a new way of developing the electric system, then in order to get good performance and good reliability, you better face up to the idea that doing this, whatever the market benefits are, may well involve you in spending a lot of money on building new transmission systems that have been designed for that purpose. Just on business, the electric utilities hold assets exceeding $600 billion. 70% of that's invested in power plants, 20% in distribution facilities, and 10% in transmission. It's one of the largest industries in the US, and it's bigger than twice the size of telecommunications and nearly 30% larger than the automobile industry. That's a big business. However, the largest individual corporate market cap in the enterprise is that of Exelon at $32 billion. A lot less. And this means that the decision to invest $1 billion or more needed to construct a major new power delivery T&D line is a big number. And this decision most electric enterprise corporations at the moment would balk at. So once again, think to yourselves, it's a big money business, but the way the money is structured inside the industry, finding that is not going to be used. Now, it's worthwhile saying, why on earth do we use electricity at all? One of the slides I took out of this presentation, and I wish I hadn't, was a Melchett lecture a couple of years ago, in which the author was commenting about why we use energy and what energy does for you and all of these things. And he was talking a lot about, in the early stages, about what he called ambient energy. And ambient energy means the energy that's just around. The wind blowing in your face, if you like, or the sun making you warm. That's what he meant by ambient energy. And his remark was that we don't even pay any attention to this because, for one reason, nobody's thought of a way of metering it yet. So it's free. And so long as it's free, then you don't think too much about it. The whole point about the introduction of electricity was that in the early stages, it looked like the first thing that had happened to modify that, of course, was fire. And then that introduced the idea of fuel. And as soon as you do that, you can get somebody to pay for it. You know, they'll buy the coal. They won't buy the warmth. so that at that point it starts to become a business, and from there on we've been going downhill ever since. I didn't say that. This is a quotation from Kurt Jaeger, my former boss, and he remarked that one of the most important things with electricity, one of the things that it really enabled, was not electric light, which is what Edison sold, as you know, but in fact the introduction of electric motors. And by 1932, electric motors provided a very large fraction of installed mechanical power. And today, I say in red, the electric motor in all its forms and sizes consumes 2/3 of all US electricity production. An interesting number, particularly when you look at the actual consumption, if you look at it in terms of what the customer thinks he's getting. Because the cooling takes up something like 30% of all the electricity that's produced. Cooling, by the way, means air conditioning, refrigeration, freezing, anything like that. Taking the temperature down. Drives of the sort that we've just talked about, but power drives of all sorts, take 25%. Heating uses 18%, lighting 16%, and what I put down here is computing, which means the digital society. 10%, that's 2001. And these are approximate numbers. So you say to yourself, how can Kurt possibly come up with this very large number for electric motors? And you look at that, and electric motors appears to be there 25%. The reason for that is nearly all the cooling, of course, is done with things driven by electric motors. And so a lot of the heating involves fans and that sort of thing, which is done with electric motors. And so that the total amount of the electricity that goes through electric motors is much higher than any one of those individual numbers there. The new issue, of course, is, everybody knows this, electricity is difficult to store. The grid system is a real-time system. What I mean by that is that when we generate electricity in the power business, we know that that electricity is going to be used somehow or other immediately. Immediately, you know. 2 orders of magnitude less than the speed of light. That's immediate as far as I'm concerned. But of course, just at the moment, we are interested in the whole idea of things where we're not getting electricity that we generate from fuels specifically for that purpose. But we can take the benefit of what are called renewable or distributed sources. In essence, we're going back to the original ambient kind of, it's ambient kind of thing that we're looking at here. And trying to use the ambient to produce electricity, once again, because of the benefits of electricity just as a means of transferring energy. And if we could store it, then new storage methods would have a profound impact on the electricity supply industry. Somebody else said that before, but if everybody started out by saying that for the whole of these 2 days, it wouldn't underestimate the importance of the whole thing. The storage methods start to look really important. And as you've heard, it can be short period storage for leveling. It can be long period storage to deal with, let's say, or medium long, to deal with the problems between night and day, as you know. And it can be even longer than that. If it would be nice, for example, if we could take benefits from the hot summers in some parts of the country compared to the cold winters in the same parts of the country. So it could be any length of time you like and any amount of electricity storage you would like. And so it would have a profound effect. I'm not going to talk much about storage here, largely because I don't have time and it's not really grid related. But I just put down things here. Pumped water is one that we have actually used for a long time, and it is part of the grid system in some parts of the world. Compressed gas was a technique that was demonstrated in Germany, first of all, and then later on in the United States on a project funded by my former employer. And however, thermal storage, for example, was used quite a lot in England, particularly for domestic heating. This was also used for differential pricing, incidentally, for the people who were talking about that in the last session. The CGB, as it was then called in England, had a differential pricing system, and you could heat up bricks in the time when the price was low, and then use the hot bricks to keep your house warm when the price was high, and that was very popular some time ago, about 50 years ago actually, but for me it's not long ago. Then on the rather newer things, mechanical flywheels, once again, in a sense, this is a very old storage technology, but it's been started to become of particular importance recently. This is a short-term one. Ultracapacitors, and I think somebody will be talking about that at this meeting. SMES, superconducting magnetic energy storage, was thought at one of the times to be one of the most important ways of using superconductivity. It's been a little bit disappointing, but I'm not sure that it's dead. Obviously, the electrochemical aspect of batteries was important, is important, and particularly for small electric devices, portable electric devices, which is a significant part of the total electric market, just not one that's connected to the grid. That's very important. And then, of course, there's chemical energy storage, which is how I personally regard hydrogen. There are other chemical storage systems, but hydrogen I've instanced for that reason. The transformation in this century, as we've been going a change, the quotation marks, usually when they appear unattributed, are taken from papers by Kurt Jaeger. But the same thing occurs in many other places. And it says, as the demand for power is growing, the nature of the electricity demand is undergoing a shift towards digital technology. Microprocessors now number more than 12 billion in the United States alone. What we are interested consequently then from the situation where we are now is to look at improved transmission capacity, grid control and stability. And this is the smart electronically controlled network about which we've been hearing. This particular slide was one that I had in 2003, and I've just put it back up again because it actually does still represent the situation now. I'm not going to talk about it in great detail because many of you were here then. I trust you remember it all. But you can see that the electronics and fully automated T&D control systems are what are required. And this is specifically about Kurt talking just this year about the digital society, and says that the local distribution systems are just the last bastion of the analog electromechanically controlled industry. And you can read it. And the business about the increasing need of electricity for people who are using digital devices in one way or another is expected to increase. As you saw from my graph before, it's 10%, or it was 10% a couple of years ago. And most of the people who are concerned with predictions come up with a number like an expected 30% by 2020. The demand for that, of power that can deal with the digital systems, is a lot more difficult, however. And the comment here that's sometimes quoted is that a fraction of a single cycle can disrupt performance, as well as the things that we're used to, transients, harmonics, and voltage surges, and so forth. So the implication is that there's a demand for generation which has that level of cleanliness. And Kurt particularly said this, keeping the lights on 99.997% of the time. That's, by the way, the requirement that we presently work to. Isn't good enough. It means that people won't have power for 2.5 hours a year. In today's impatient, increasingly computerized world, that's more than just a nuisance, he says. I want you, when you say this, I want you to think back to that list of uses of electricity by the ordinary person, by the customer, when you're thinking about this. Yes, indeed, it's likely that there is going to be need for electricity having this kind of level where we can control it to not having as much as a quarter cycle variance, and that kind of thing. But you'll see, if you remember that list, you'll see that all the things above that 10% at the bottom I don't really care that much. These lights, for example, above us are flickering already. Some of you can see it and some of you can't. But the thing is, if they flickered a bit more or a bit less, you wouldn't really notice. It has to get down really quite low before you start to notice flicker in the lights. And that means that for a lot of these purposes, heating, domestic heating, your refrigerator, let's say, things like this, don't actually require anything better. They don't require anything better than 99.97. If your freezer's off for a total of 2.5 hours in the year, so long as it isn't all at once, then it's not going to do you any harm, and you probably won't even notice. You have to reset your digital clocks, of course, but the rest of it's okay. So that when you're talking about a digital society and the demand on the new electricity and the new thing, you have to think very carefully about what you're going to do. My personal view on this, by the way, is that you can charge people different prices for these things. If somebody really wants digital power, I think the best thing you can do is charge them a lot of money for it, because if they really want it and it's that important, they'll pay it. Furthermore, that'll overcome our problem we talked about before about the inadequacy of funding to upgrade the system. If you don't have to upgrade the whole system to that level, fine. The total demand for money in that case is nowhere near as frightening as it would appear in the first place. So, you know, you always need to think about these things, about what your user wants and expects and is prepared to pay for. I'm going over these because you can read. I'm waiting to find if there's something important I want to tell you. Yes, okay. Critical capability gaps, interconnection standards and integration guidelines for distributed resources. And, of course, we heard about that, and there's some work going on at that at the moment. Technologies for short duration ride-through capability. Backup generation and storage systems. DC microgrids. Power quality solutions on the customer side of the meter. And then here, these are the objectives for the new century. Real-time power electronic controls. We need systems that would be self-healing. And we also need to look at how we're going to handle distributed energy resources. And we see here the comment about seamless integration and so forth. And the fact is that at the moment, we can't really do that. Okay. This is one of the things that came up. I put this up because it's a pretty picture, and it just shows you we have hit the real time. And this is the business about the energy web. So the whole point about this thing at the moment is that everyone is wanting to have an awake, responsive, adaptive, price-smart, eco-sensitive, real-time, flexible, humming, and interconnected with everything else. And that's what we call the energy web. And our object, I think, is to try and achieve that. And Rick would have liked that, I think. Thank you.
We're open to questions. Everybody's doing over lunch?
Wake up. Lunch it up.
We'll move on to our next speaker. Rush Robinette, and his title is Energy Sustainability.
So let's see. Actually, I changed the name a little bit to call it Exergy Sustainability. So let me give you some background, give you an idea of my specific filters and biases. I noticed that there's a lot of different kinds of people around here with a lot of different ways of looking at it, so I wanted to lay mine out specifically. Before I go down this list, I need to give you one more. I went to school both at Texas A&M and the University of Texas at Austin, so I have this unique capability to hate myself. And so for those who have good Texas Aggie jokes, I would appreciate them around lunchtime or dinner maybe tonight. I'm always looking for new jokes to tell my friends back at home. They seem to get a real entertainment out of giving me a hard time. I'm from a background that's very different than many of the people around here. I came through the aerospace engineering program, and so the way I look at the world is through dynamics, controls, optimization, and everything is time dependent to me. It's path dependent and time dependent, and evolution is very important to me. Irreversible paths in thermodynamics don't exist in my mind. I look for these driving and dominant input parameters. I want to be able to design a control system that's very simple. And when I look at these complex interacting systems, they just don't make sense to me because I don't see something that I can get my hands around. So I look for these single points of failure. I'm trying to apply this to self-organizing complex adaptive systems, and that's a big buzzword, but my background came from robotics. And we demonstrated that you didn't have to build robots that were smart like people. You could take simple, dumb robots, make them work together in a team, and produce some amazing results. There were some discussions earlier about the inherent redundancy in distributed systems. When we built these distributed robotics, there are some serious failures that can occur in those teams as well. If you can find the right spot, you can, in a sense, fracture the whole group. So you have to be very careful how you design these systems. The fundamental driver that I found was Exergy is the elixir of life. So I was thinking, how could I do this like Monty Python would do? And bring in this goblet that says, here's this holy grail, and join me on this. But Exergy is that portion of energy that's available to do work. Not all energy can do work. And elixir, I found this definition in the encyclopedia and in the dictionary. It was perfect. Prolonging life indefinitely. It reminded me of when you were in school learning about Ponce de Leon, looking for the fountain of youth. And so sustainability matched up just fine with that. Well, how am I going to actually explain this? Well, I go looking for the fundamental laws of thermodynamics, and I get these insights that say energy is constant in the universe, and entropy is always increasing. Well, that's nice, but for everybody kind of sitting around the table, they're like, what is entropy? And those who had their first thermodynamics classes probably ran away, wanting never to see it again. So you say, okay, well, let's look at it from a different point of view. Energy can't be destroyed or created, it just changes. Now we're getting into something interesting. There's this idea about availability and unavailable energy, and that these have to follow this. That's still not really driving it home yet. Now we talk about poker, and since poker is on ESPN now, I can actually get my hands on this one. And what I find out is that these insights tell me I can't win. I can't get more out than I put in. I can't even break even because I'm going to lose something. And what's even worse is I can't get out of this game. I'm stuck. So the question is, what am I going to do about this? Well, now that's where I'm going. Is I get this confusing message when I talk to economists. I mean, I'm confused about it at the beginning, but this even confuses me more. I'm looking for this scarce resource. Energy is conserved, so it can't be a scarce resource. Exergy, on the other hand, can be consumed and degraded, so it can be a scarce resource. But the question is, why? So depending upon how you look at these hurricanes, you look at them and you say they're going to come and wipe you out. I look at a hurricane and say that thing is stored with exergy. It's this wonderful mechanism that nature has to take all of this solar energy and basically concentrate it into this area. So wouldn't it be great if you could actually have a mechanism that every time you see a hurricane come by, man, I'm going to suck the exergy right out of that thing and power all these places. So just like my friends say, exergy is everywhere around you. The only problem is that we're not quite smart enough to figure out how to get it and use it and change it into work. So let's take it a little bit further and look at another confusing problem, the difference between first law efficiency and second law efficiency. And I'm specifically looking for an optimization process here, something that's interesting to do. The second law of efficiency gives me something to grasp onto. It says, what is the amount of available work required to do anything versus how much do I use? So I always think about this in my house, and it always makes me question why I continue to do this, but I heat my house with propane. I live out in the woods, and I have this propane tank. I degrade that propane down from its high exergy content, low entropy, to this low-grade heat, and I waste all this exergy in it. I don't ever take advantage of it. So in that concepts that have been discussed around here, one of those things that you could talk about is how do I more efficiently take some fuel like that and use the exergy that's really there? Or how do I tax the exergy that's not being used? that'll make people start to pay attention because there's something there that they are actually running out of. So now the question is, what am I going to do about this optimization process? What's at stake that gets people interested? Well, it's your survival of your lifestyle. It may not be your life, but it is your lifestyle. If you look at New Orleans, there was a mix of life and lifestyle there. But here we're talking about everything that's in this picture. Of course, I had to stick the X-15 in there since that was my inspiration to become an aerospace engineer and would never have happened if I didn't have this Exergy available to me. But everything in that picture that you see is touched by fossil fuel today. Everything, including the foods you eat. It's a source of Exergy. So all of these things are Exergy, and they're everywhere in your system. And so I'm responsible at Sandia much for renewable energy, and I'm trying to find a way to get people to want to use it, want to engage it. And once I start seeing that fossil fuels are everywhere, the question is, can I hook into those? Well, cheap fossil fuel is the elixir of life that we have right now. So is there a replacement? Present infrastructures are designed for fossil fuels. The storage is in the fossil fuel. You don't have to have storage on the grid if you set it up properly and you generate power on demand. The storage is already there. So the question is I can change the storage in lots of different places. The question is, how do I do it and what should I do? The goal is a long-term predictable business plan. Of course, we'd all like to be able to predict the prices. We'd all probably be retired by now and we could all go have fun on the beaches, but that's the goal. So we go back to this idea of, I call plug-and-play power of all Exergy sources into a flexible adaptive infrastructure. That's what I'm really after. Now the question is, how am I going to do it and why would I do it? Well, people have pointed out to me that I say things inappropriately in the appropriate crowd, so I'm going to call people Exergy parasites. We live on this host called the Earth, and we're just going around trying to grab Exergy, and we're trying to order the environment around us. So in the case of the autonomous rover here from Mars, the most important thing is to keep that rover moving, keep it up and going. So the best source for that available to us today would be the sun. There's an impedance mismatch, though, between the source of the power and the use. So we stick a storage capacitor in there. We live with the duty cycle that's implicit there. That thing can't run all the time. So you run it, you run it, you run it, and you stop. You run it, you run it, you run it, stop. Now I make the analogy to people. We have this, some of these fossil fuels are directly from the sun, some are not. But in essence, the analogy says, I've forgotten all about where the source comes from. All I'm paying attention to is what I'm digging up. So eventually the question is, what's going to happen with the duty cycle? I'm not going to predict it. I'm just making an observation. So there's the impedance mismatch. The impedance mismatch has enabled us to overcome by fossil fuels, enabled us to do a lot of things that wouldn't happen otherwise. So why Sandia Labs? Well, we have this history in nuclear weapons surety. If you know what Sandia does, the goal was to not ever let a blinding white flash occur accidentally into the future. So I was looking for a connection between what we do core and what would happen in sustainability. And that's the bottom line. In the context of the long term, you want to have, in our terms, it's don't let this happen. In the terms of business plan, it's be able to do predictability as much as you possibly can with a completely uncertain environment. Okay. So why is it so hard? Well, one thing that becomes obvious is when you start working through entropy and Exergy and all these terms, you find out that one need you need to have is to find and harness Exergy. The second thing you immediately do is degrade it. You eat it, you do something with it, you convert it into something else. Some people's entropy is other people's order. Just depends on how you say it, how you describe it. But the question is, how do I create order and disorder over time in an optimal way? So those familiar with Built to Last, Good to Great, Jim Collins, Tyranny of the Or, Genius of the And. For those familiar with Abraham Maslow, it's called Transcendence of the Dichotomies or Dialectic Synthesis. For those who are familiar with your farmer, they understand what it means. It's called the farming cycle. What happens if I get it out of cycle? Well, I kind of die, especially if I'm a subsistence farmer. If I'm going to do an optimization problem, I need a multi-criteria. and I need at least two competing factors to make this an interesting problem. So I'm going to pick short-term economics, cost and profit, and a long-term sustainability argument. So the question is, how do I do survival and predictability of the future given all this uncertainty, all this chaos? Well, one is live for today while planning for the future. But in the end, what I'm really after is I'm going to go up through here. I'd like to look at what all of these different options are. And in the bottom line, it's what do you value? What is it that's important to you? So I showed the one for the Mars rover. Sustainability was what was important. It was number one because you wanted to keep that robot running as long as you could, to do as many experiments as you could think of. And as time went along, you'd like some flexibility to go look at that rock or go look at that rock, whatever the situation would be. So what's been discussed all along here is that same question. What do people value? What do they want? What will they pay for? What's the highest priority on their list? Well, I'm going to propose one way of doing this, and it's a transition plan for your lifestyle support system. The lifestyle support system is your infrastructure. I'm not talking about just the grid. I'm talking about the whole infrastructure. And the question is, can you get storage and these interconnects all through the infrastructure? Are there ways to do that? Well, one way to do it is to do what we call hydrocarbon intermediary. You might also call it synfuel. But synfuel, it's not the idea of taking your biological sources and do it. You're actually going to find persistent sources. So persistent sources are renewables, nuclear power, if done properly, for example, with reprocessing. Also looking at clean coal, if you can work it properly. But the problem with clean coal is that if you end up using it for electricity generation, it's about 400 years worth nominally based on resources we know about. If you start doing transportation as well, it drops down to about 120 years. So we arbitrarily chose 200 years, so we went from something that was very sustainable to something that was unsustainable based on our metrics. So what would this look like and how would the step be? If you look at conventional synfuel production using hydrocarbon fuels as the source, there are all these paths that were analyzed and done already, and it connects through the infrastructure, all through the whole thing. If you replace those upper parts with a heat source and water and carbon dioxide, it's potentially possible to do the same thing. And now what happens is that your fossil fuels become synfuels, and the synfuels become working fluids in the system. They're kind of like your Freon in your refrigerator, except now it's a chemical process. I'm trying to emulate one of the only sustainable systems that I think I understand is sustainable, and that is life in this biosphere. And so we have this energy carrier that's ordering up and carrying energy around, and it cycles through and brings these masses back together. So this is a path to go through it. And now what you're talking about doing is the heat comes from a nuclear power plant, comes from a concentrating solar power tower. You can begin to use water out of the ocean. Carbon dioxide, you can make a start transition where you begin to take the carbon dioxide out of a coal burning plant. Instead of doing sequestering with it, you turn it into a synfuel. Or you end up going through this path and you start talking about using carbon dioxide out of the air in the long term. So you start sucking it out of the air and you close the cycle. So now you begin to do something that looks like carbon neutral process. Part of the reason this came up is one of the smart Alex that works with me said, I asked him a question, how do you store hydrogen? And he said, oh, the best way to do it is attach a carbon molecule to it. That makes it real easy. And in fact, it makes it simple to use the infrastructure. So even though the efficiencies may not look all that great on some of these processes, when you start throwing in this huge infrastructure that's all this huge cost to replace it all, the game gets a little more interesting. So the long-term idea here, and I apologize as the charts went by, they got more cluttered with words and things. What's important is the top part up there. We have open cycles today. To move towards this process we're talking about in this future, you'd like to take one step and go to a closed reversible cycle. It's an ideal system. It's what's identified in equilibrium thermodynamics. You're not going to get there because every step has some irreversible aspects to it. But it's something to target. It's something to look at transferring the exergy through the system as efficiently and effectively as possible, which means you begin to match the exergy source to the exergy sink. You begin to most effectively use that scarce resource that's in that energy flow. Then you move to closed sustainable cycles. I picked this hydropower because it gives some nice features. It's connected through, you really are showing your parasitic nature now. You're actually just cutting yourself right into this, you're transducing this gradient that you've identified. And the dam eventually gets filled up with silt. So you have to deal with that irreversible entropy production mechanism. So if you use a sustainable source of persistent energy, or persistent exergy in this case, you're shedding that irreversible entropy production to a sustainable source, and it's not affecting the bottom line of what we're talking about, the stored exergy. So the possibility is you can store more exergy than you use as opposed to just depleting it like we are right now. On the other hand, the long term would be nice if we could do fusion, but we got to do something between now and then. The other part of it's interesting as well is that if you could tie yourself to deep space, all this ambient energy that was described just a little earlier, you could generate huge amounts of power out of it if you just dump it to a colder source. But again, we dream. So that's basically it.
Open the questions.
So how does something like ocean thermoelectric generation work and fit into your exergy scheme? Is that a good example?
So it would depend on if you could generate a large enough heat gradient, like we do in solar power towers, then it's possible to do thermochemical conversion processes. And if you generate the hydrogen, everything from there on is a downhill process. If, on the other hand, you can't get those temperatures, then you can go to electrolysis, but you know what the kind of efficiencies those are. So what it boils down to now is that if you have a source, I'll pick one like that I'm a little more familiar with, say the Aleutian Islands, where you have a large number, like you have large geothermal deposits. If you want to get that exergy to somewhere, it's potentially a possibility to go and collect that exergy in the form of the synfuels and bring it to wherever you want to use it. So if you have the same kind of situation you're describing, it may be possible to do the same kind of thing. But the question still comes back to is, will people pay for it? Can you actually make it useful? Because we're right back to the same thing. There's exergy all around us. The question is, can you harness it? Can you get a hold of it? And will people recognize the value of it? In that case, you may actually have to tie up what the costs would be in these hidden externalities that are hidden in there that you have not identified. And so what are they and what are the costs of them? And so it all boils down to, is there a cleanup issue if you use some other source in its place? So the argument always comes back to, do you do something because you can and because you know how to do it, or do you do it because there's some other reason for it?
I'd just like a little more detail on the actual converter. I mean, you're getting a solar thermal tower, and you've got water and vapor, and you've got CO2. So tell me a little more about it.
What you're looking at is let's see, right now what we're looking at is sodium iodide catalytic cycles. And so you're bringing in the water, you're running it through, in the case of what we're looking at as a two-step process of going through a catalytic process of breaking up the hydrogen, doing intermediate, some nasty acids that you're actually going to produce. And so in some sense, if you ask the environmentalists to bless this thing, they might actually choke a little bit on it the first time because of the kinds of catalytic materials you're using to produce this output. There's also some options where you can cut off one of those catalytic cycles and replace it with an electrolysis step. So it just depends on which cycle you'd like to do. For solar hydrogen production, I think the last time I was talking to the people doing the detail work, there's something like 100 different options for what the catalytic cycles would be, and they're trying to go through those to determine which ones would be most efficient at about 1,000 degrees C. Unfortunately, when you start talking about the materials issues, which we come right back to the nanomaterials again, how many of those materials are going to survive in that toxic environment under basically high pressures and high temperatures. So there are plenty of nanomaterial issues that come up if you really are going to make these things happen, where you produce hydrogen using these kind of thermochemical processes.
More questions? If not, hold on. Thank you. Our next speaker is speaking on superconductivity, nanotechnology, and energy, Paul Chu. Paul.
I would like to dedicate this talk to Rick Smalley, who is the inspiration of many of us here today. As I always said, some people ask me, where do I spend my time? As you can see, I spend my time in 3 different places. And then when I'm not in Houston or not in the United States, I spend my time in Hong Kong, as you can see here. And this Hong Kong, this Kowloon, when you go beyond that place, and that's where our campus is located, Hong Kong University of Science and Technology. And then when you look from the ocean, it looks like this. And then when you look from my office, it looks like this. So all of you are welcome to visit the university when you have time. Today I'm going to talk about superconductivity or superconductor. It's a nanomaterial, as Rick Smalley always mentioned, because you have to control it to the atomic level in order to make use of this material, wonderful materials. Basically, there's 3 properties. One is the resistance drops to 0. As a result, you can use this material to transmit electricity over a long distance. And then the second property is it has a repellent magnetic field from itself. As a result, you can flow something on top of it, and therefore you can use it for electromechanical machineries. And the third property is macroscopic quantum phenomena, and therefore you can use it for ultra-fast switches and also ultra-sensitive sensors using it. But in order to reach this superconducting state, the temperature has to be lower than the so-called critical temperature, T sub C. The current density going through the material has to be smaller than JC, and the critical field has to be smaller than the critical field. Basically, we all know now whether it's high-temperature superconductor or low-temperature superconductors. We know that usually for material, and the electrons go through the lattice, and therefore they bound into each other. So therefore you have resistivity. But if by polarizing the lattice, and one can actually get these electrons going through it, and they form pair because there will be attraction between them. As a result, all these pair electrons will go through it as if they are not being scattered. And that, in other words, finally, as if they are moving in nothing, in vacuum. And that's the situation. That's why you don't have resistivity. And that's why, because a little while ago, when we talked with the Dalai Lama, I said, superconductor finds its common ground with His Holiness. The reason is nothingness and harmony. As you can see here, when people gave Dalai Lama a birthday gift, it's nothing. He was so happy because a box with nothing. So therefore, superconductivity, the electrons do not see anything. It's nothing going through it. It's also in harmony. But anyway, right now we know there are more than 150 non-intermetallic compounds with TC greater than 23 degrees, and that's usually used it's arbitrary, okay? It's the line drawn between high-temperature superconductors and low-temperature superconductors. For all the high-temperature superconductors, with a TC higher than 77 degrees, that's the boiling point of liquid nitrogen, and belongs to a class of material which is it's a layer structure. It's layer cuprates. And right now, the highest transition temperature is 134 in the mercury-based material. And at ambient pressure, if you squeeze it, it goes up to 164 degrees Kelvin. The JC can go above 1 million ampere per centimeter square at 77 degrees, and the critical field is huge. And then the surface impedance is also very, very low compared. It's equal to the superconducting niobium material at 7 degrees, while the high TC material is 77 degrees. Compared with copper, depending on the frequency, and it's about 10 to 1,000 times better. Now, when you look at the TC, this is how it goes. The transition temperature has been climbing very rapidly, up to 164, as you can see here. It's plotted as a function of time. But for the last 18 years, lots of study has been done. Basically, it can be summarized by 2 very simple phase diagrams. One is this, when you see all the materials usually starts out as an insulating antiferromagnetic material. When you dope it, it becomes metallic and becomes superconducting, as you can see here. And then there are lots of physics involved here, but I'm not going to get into that details. And also when you look at the magnetic phase diagram, it's quite complex, but this is extremely important for application. It's also very rich in physics. Basically, this is so-called HC2. When you go to this region, it's useless, this material. In between here is not very useful. It's useful only when it's in this region. Now there are some questions on HTS, high temperature superconductivity science. Basically, what is the mechanism responsible for high temperature superconductivity? And is there a comprehensive microscopic theory? And do HTS or high temperature superconducting materials form a class of materials of its own because it cannot be described by the conventional theories up to this moment? At least most of the people think so. And also, is there a room temperature superconductors? All these things are unknown at this moment. Now, ideal superconductors, high temperature superconductors for science and technology is that we would like to see the TC gets higher. And if we can do that, we can test the theory. We can also, for practical application, it becomes more efficient. And we like to reduce its anisotropy because all these materials are layer structure and the current flows better in one direction than the other directions. If we can reduce this isotropic properties, then essentially we can make the material, the application much easier. Can we broaden the material base? Right now it's oxide. If we can get into non-oxide materials, then we can build hybrid devices with semiconductors, which usually are processed in reduced atmospheres. And also, can we improve its chemical homogeneities and also stability? High TC are not at this moment. Can we enhance the flux pinning? I'll get back to this point and see how nanotechnology help us in that respect. Well, in order to get higher transition temperature, for example, we know this material is extremely unstable, and therefore, can we lock in some unstable phases? One of the possibilities right now, many of these materials are processed in high pressure, and then you get it out and look at it, But could it happen when you release the pressure, some of the phase already disappears? So we developed the technique in here. It's the diamond cell here. So you squeeze material on this tip under high pressure, and you measure it in situ here. Basically, the system looks like this, and then you use laser beam to heat it up inside here. You form the material, you measure it in situ here. Hopefully, we can get it working. Right now, we just got the system working at this moment. The material is interested by the general public is because of its potential applications. Right now, for example, for a cellular phone base station, if we use this material as a base station, and actually it can increase the range of coverage. And also you can make more efficient use of the bandwidth. And then you can also use it for magnetocardiogram. For example, in this case, this is our student, and you can put the squid inside here, or the superconducting devices, superconducting quantum interference devices. We call it squid here. It can map out the magnetic field above the chest, and you can see here. It turns out in this region, it carries lots of information. Let me just give you an example. In here, this is myself before using myself as a guinea pig. I checked it out. People told me my heart was very good, And now you can see, this is a magnetocardiogram, and then you can use a dipole model, calculate the pattern here. Another of my friends who also feels pretty good, but he has problem, and is under medication. When you look at ECG, it's the same like mine, but you look at the MCG, magnetocardiogram, they are very different. So it does carry some information that ECG will not show. It also, you can also detect the fetal status of this young lady, for example. Usually in certain periods, when the fetal developed, and no procedure can reach it unless no non-pervasive intrusive method can detect it. But once you use this, using MCG, you can detect it here, the mother's heartbeat, and here's the fetus heartbeat. And then it carries lots of information, and you can analyze and get lots of valuable information. I should mention this was done in Germany. The previous one was done in our center. And then my colleague also used superconducting wire, and then you can do MRI and look at this poor, because usually when you try to look at the injury of the spinal cord, you have to embed copper coils and embed it under the skin. And then in this case, we don't have to do that. Just put it into a styrofoam cup filled with nitrogen, and then you can actually do imaging, which is much better than the copper coil, in this situation, as you can see, and also image the brain here. And then, of course, you can use it for flywheel because you can lift the flywheel here by the superconducting magnet combination here. For example, in this case, it's only 42 pounds. It's small. But when it rotates to 6,000 RPM, it takes about 6 days for it to spin down. But if you use conventional bearing, 15 minutes, it will stop. Okay. And now you can see lots of application prototypes, devices have been demonstrated, and motors and also cables, and this is transformer, and also some of the power quality control system. This was by American Superconductors. You can see it's already demonstrated. So many prototypes, as I just mentioned, have been manufactured and tested successfully with performance better than their conventional non-superconducting counterpart. But we believe that its major impacts of high-temperature superconductivity will not be felt until power applications of this material becomes a reality. Now, for example, let's look at traditional path for industrialization. And this was given by Xu Guangdi, Professor Xu Guangdi, the president of the Chinese Academy of Engineering. And he said when you plot pollution as a function of time, usually it goes through this bell shape, as you can see here. And so every country originally was poor and clean, as you can see here. And then when they industrialized, generate lots of pollution. And then finally, when they get rich and they realize the environment is important, they started paying attention, coming back. The goal is to reach the region of rich and clean. Okay? And China right now is at this point. It's very serious. So they're worrying whether they can develop a tunneling model in here. Going through here, if China were to follow this path, the world cannot sustain it, okay, as we all know, the situation. There are many reasons. As a result, people now are talking about a new 4R sustainable development for the new millennium. As that the first thing is to reduce consumption and reuse the material, recycle the material, and also remanufacturing, doing all this kind of things. Of course, now let's look at here. You all know electricity is very important. I just show you Asia, the map of Asia at night. I think probably some people don't pay attention to it, but you can see here this Taiwan, this is the coastal airline, the coastal line of China, and this is Hong Kong, and so on. And now there's one area missing here, and that's North Korea. You can see it. So therefore, it's very easy to see that where there is light, that is electricity, there is prosperity. Now, the challenge for the electrical system, I think we all know, is generation, transmission, and storage, as I already mentioned. To me, because I'm working on superconductivity, I have to say that transmission is the most important of all, at least for the short term. And high-temperature superconductors may be the solution for the solution for electricity transmission, generation, and storage because of its high efficiency, high capacity, and also it can improve quality. For example, the DC interconnect, when you have a blackout, it can come back very quickly, and that's for mismatch relief, fast response to blackout, and so on. Now, Jimmy Gladfeldy actually was the starter on this. Said the U.S. need an energy superhighway to transport large amount of energy, the lifeblood of our economy, to the population centers over long distance. So Jimmy Gladfeldy envisioned in 2001, I believe that's about the time, that it should be energetically efficient, economically competitive, environmentally friendly, technologically advanced, safe, and secure. That's what we like to have, a system. So then, at the time, it was proposed to build a super cable. And basically what you have is inside here, you have cryogen flowing through, and that can be hydrogen, it can be liquid nitrogen. And then you have superconducting material here to transport electricity. If you use liquid hydrogen, it comes out with hydrogen for transportation purpose. Now, that's his grid, super grid, as you can see here. And so you have a national grid and regional grid and microgrid and so on, and then put in and make it intelligent, all these things you can see. Well, so the promising, when I looked at it recently, because I'm located in Hong Kong at this moment, so I look at these problems recently more carefully, it appears to me the most promising countries for the deployment of high-temperature superconducting power transmission lines probably is the developing country. It's not the developed country, although the U.S. needs it at this moment. If, for example, Japan is very advanced. When I talk to them, actually their grid system is overcapacity at this moment because after they try to promote energy saving, going like that. So developing country, it's in greatest need, and China is in a unique position, and also it's a unique position to harness the HTS technology for power transmission. Well, for example, you cannot read all this. This is from the Bureau of Statistics, and you can see the electricity consumption between 1990 to 2002 increased more than threefold, as you can see here. And also lots of waste in the transmission, in the whole process. It's about 7 to 8%. I just listened to the previous talks. Later on, maybe for this country, it can go up to 9%, 9.5% when we use it heavily. But at least for the Chinese right now, it's 7 to 8%. If we can save, that translated to about $50 to $60 billion per year. If you can save a fraction of that, it will be a great saving for them. As a result, they don't have to build so many power generation plants. And if you can then solve some of the storage problems, and they can also integrate to make better use of the renewable resources, as Jimmy Gladfeldy previously pointed out. Maybe not in this meeting, but in other meetings. And let's look at the Chinese. For example, when you look at their steel production at this moment, okay, and it's #1 in the world, in this world. And then when you look at their ferrous metal production, again, it's #1 in the world at this moment. And when you look at aluminum, #1 in the world. And when you look at magnesium, which is appearing is very important, also #1 in the world. When you look at the rare earth shipment in the world, #1 in the world. When you look at one of the very important material, that's light, strong magnet, that's the neodymium iron boride, for example. And again, it's the largest in the world. All this is done with a big price to pay, because the Chinese technology is backward at this moment. And their energy consumption rate per GDP is 3 to 11 times compared with the developed countries. And when they use so much energy, and not just wasting energy, but also degrading the environment. Okay. So therefore, it has serious impact here, not just energy, as I mentioned, environment, and also social situation, and also international relationship, and so on. Recently, there was an article written by one of our faculty members at Hong Kong University of Science and Technology pointed this out. How can the how can Chinese avoid this conflict with the Western world in terms of energy consumption? So the Chinese is paying a lot of attention to that. If you look at the energy distribution of China, and this is oil, and then this is coal, and this is the gas, and then hydro. They are all distributed in this part of the country, and yet the population center is all in this area. So therefore, transmission becomes important. So what I did is that I said, can we do the same thing by just transplanting the Jimmy Gladfeldy's super energy highway, super highway to China. So you build a backbone, and then you build the regional grid, and then you put in the microgrid, and then you put into the intelligence. That's what they can do, In fact, they are seriously considering this part at this moment. And I should mention to you, I just got a call yesterday, and they are going to put in something into the Olympic Village, as demonstration model. I just got that approval yesterday, from the Olympic thing. So at this moment, HTS is ready to meet the challenge. Well, I do have a few more things to do. With the present technology, it can be used if we can overcome some of the psychological barriers and so on and so forth. I think China is ready to accept that challenge at this moment, even though maybe in a small way. Can we do more and make HTS more appealing for commercialization? I believe we can do that by increasing its performance and therefore to reduce the cost. by increasing the JC, the current carrying capacity, and by increasing the TC, if we can get it to the point that we don't need cryogens, that would be great. And also speed up the processing, reduce the manufacturing cost. Let's see how nanotechnology can help. For example, it has this layer structure, and therefore the pinning power is small. What do I mean by pinning power? Basically, when you apply current going to this direction, there will be, this is type 2 superconductor, so therefore there will be magnetic field line going through here. Because the interaction between them and the field line will move in this direction, there will be, whenever this field line moves, there will be loss even for a superconductor. You want to reduce that loss. How do you do it? You try to pin it down, so therefore the fluxoids will not move. And it turns out there are some interesting things. So we would like to put down some defects of the size of the coherence length and also high density to do that. But for high temperature superconductors, the coherence length is very small. So therefore, in order to produce that little defect to pin down the fluxoids, the conventional techniques cannot do it, to introduce such a small defect and also with such a high densities. So therefore, people talk about using the new nanotechnology to do it. For example, we can do it with high temperature superconductor and non-superconductor as a defect, and also doing multi-layers and nano-decorated substrates and doping and also irradiation and so on and so forth. Let me just go through it very rapidly to show you how it's done. For example, in this case, it's a multi-layers. They have YBCO material and put on top of the so-called 2-on-1 materials. As you can see here, the critical current density is enhanced by a factor of 5, okay, you can see here. When you do it, and the current carrying capacity is increased in the presence of magnetic field. And then when you do it the other way, is to decorate this thing with some defects, like a YBCO, the insulating defects in this case. In other words, you first put some nano defects on the substrate and then put the superconducting tape on top of it. Now you can immediately see that the current carrying capacity is increased, by a factor of 5 or 4, something like that. You can see it. Then you can also do it another way and put some metal, nanodots on the substrate. Put the superconducting material on it, and then you can see the critical current density, current carrying capacity increased by a factor of 10 in this case. And you can also do it by layers, and this was done in our lab, and you can see here just by different materials, YBCO, and then put another doped YBCO on top of each other, and induce some defects in it. And because of strength, and you can see the JC also increased tremendously in this case. In addition, you can use neutron irradiation to do it. Usually the neutron source is expensive. So my colleague, Wei Kan, developed a method. And essentially what you do is you use, because this material has barium in it, you replace some, you dope it with some boron in it. The boron attracts the neutrons and decays, and then it generates neutrons. It's very cheap, and just thermal neutrons, and creates defects. As a result, the JC also increased by a factor of 20 in this case. You can see here, you can increase by that. So now, how can we speed up the process? And my colleague Salama did the following. He said, let's use a powder precursor for these things, and he can improve the substrate of this tape, and he can also, the mechanical properties of the tape, he can also speed up the reaction time. And for example here, and you can see this, the strength increases, and also for these tapes, and he can do it very quickly and pass large current through it. So now the final thing is, we talk about room temperature superconductors. Of course, this basically is relative. I remember when I was a student, I asked my professor where to find whether room temperature superconductor exists or not. He said, yes. I said, where can you find it? He said, go to the edge of the universe, the residual radiation, you can get that. But now, of course, you don't get it. You don't have to go that far. In fact, there was an announcement that the first superconductor that works at room temperature, and actually that was given to me when I gave a talk at Washington, D.C. It turns out this was a symphony orchestra superconductor, okay? Of course, it has to work on that. Oh, this is strange, it changes color. So now, can we continue increase the JC and the critical current density? It turns out we can, I think. Well, the basic idea is can we find a material which has negative dielectric constant? Okay? If we have negative dielectric constant, then the electrons will attract. When the electron attracts, they form pairs. When they form pairs, you have superconductivity. So can we do that? It turns out, indeed, we found dielectric constant when you apply an electric field for the nanoparticles in a specially treated way, it goes to negative, okay, in this case. So when we went through the analysis, it shows that there may be some collective modes happening there. And then whether it's superconducting or not, we still don't know, because I should mention all this happened at room temperature, okay? So we are now trying to definitively determine whether something is happening in here. But so with that, I will conclude my talk. And thank you very much for your attention. Yes.
You didn't say very much about storage. Is there some hope for superconducting storage?
Yes, I think basically many people think it has hope. But just yesterday, I talked to Gregory Urich, and he said there's no hope. Economically, it doesn't work for that case. But I'm not so sure at this moment, because particularly when we get the high TC, the temperature higher, the cryogenics is going to be reduced, and then get the fuel higher. Then basically, it's basically the h squared over 8 pi energy density. If we get the fuel high, then there's a chance.
Paul,
Yeah.
or perhaps someone else in the audience could chime in. Do you have an estimate of how much of the national energy budget would be saved if you hypothesize you can eliminate in all the transmission lines, all the motors, the resistive losses?
No, I don't have a number. And I believe someone probably has an answer on that. I don't. Jimmy, do you have one?
I admit someone was talking to me, so I didn't hear the question.
John?
If you eliminated if you had a room temperature superconductor that you hypothesize could eliminate all resistive losses in transmission lines and in motors, because we heard earlier that motors consume a lot of our energy budget for the country, how much total energy as a fraction of what we consume would be saved? I don't know the answer to that.
But I look at the previous number without referring to the motors. And because right now our transmission loss is 5%, maybe a few years ago, 5% to 7%, and now they expect it to go up to 9.5%, then one can get a number on that. But for the Chinese, in 2002, the saving is $50 to $60 billion in their price, based on their price, not the U.S. price. That's just the transmission part.
Just one simple way to get an estimate would be, I think in motors, you mentioned someone mentioned it was about 34% of the energy, around 30% of the energy in this country was being used for. And then you said if you throw in refrigerators, that are the motors in refrigerators, you get a larger fraction. And then say, wildly, optimistically say that, well, your efficiency is no greater than 60% right now, then it seems like that's a hell of a lot of energy.
Yeah, I think one issue with superconducting motors, though, is the application, depending upon the cost. Superconducting motors are great where you need to save weight. But relatively, if you have motors that are in constant, like in a refrigerator, if there's a major cost differential between an HTS motor and a regular motor, they likely will not go to an HTS motor.
I wanted to address the wish-for world. In other words, I realize refrigerants, all this, the energy, the economies can go away very quickly. But as far as formulating goals for the future, I think it's, if it's realistic to think in this way, to have this big, I think it is a big energy number, then there could be a limit, if you had the materials that Rick Smalley's been wishing for, that in terms of nanotubes or superconductors that have very low resistive or near no resistive losses that and could be made cheaply, that this would be something really just focus a lot of government dollars on.
Let me just...
Forgive me, but large motors, the big ones, are very efficient devices. The total losses in those are very small. So consequently, although they operated at well above 90%, 95% efficient, the small ones don't, of course. But it seems to me that if you're going to use superconducting technology, you'll most likely use them for large motors. I've been involved in the past with demonstration large superconducting motors, and the outcome of that was not very profitable. We also looked at large scale generators, superconducting generators, and the benefits do not come really in the energy balance. In that particular case, as you heard, it's the size. It's the size that's the benefit.
That's right. Like on ship propulsion motors, it's savings. It's not a matter of the cost of the motor. It's the savings of the fuel. The one thing that I might say about being such a large number is one thing that we struggled with at the Department of Energy, and EPRI helped us with the numbers, were how can we quantify the benefits to the consumer if we achieved even a portion of Grid 2030? And the number is so staggering. It's so huge that it's almost unbelievable. It's like, well, why aren't we achieving some of that today? And it's hard. I mean, we have to break it down because the numbers are so huge. You know, we could save $95 billion a year with just grid-wise, which was just the smart distribution system. Well, why isn't anybody doing it? That's a huge amount of money. And people it was very hard to get them to comprehend the fact that these savings were so huge.
Well, at that point, can I suggest we carry on some of the conversations in the break?